What if I told you that right now, thousands of space rocks are trying to hit Earth, but almost all of them get vaporized before they even say hello? So which one actually survives? And why does it matter? Stick around because the answer involves fire, fragmentation, and one very lucky space pebble. First, let's clear up the naming chaos. Asteroid, meteoroid, meteor, meteorite, they're not synonyms. They're stages, like a cosmic butterfly, but with more explosions. Think of it like this. An asteroid is the parent. A meteoroid is the kid who runs away. A meteor is the kid screaming while on fire. And a meteorite? That's the kid who actually makes it to your backyard. But here's the twist. Becoming a meteorite is basically winning the universe's hardest obstacle course. And Earth's atmosphere, it's not a welcome mat. It's a wall of fire.
Welcome to the atmospheric gauntlet. 3 bosses, 1 shot. Boss number 1, ablation. That's science speak for melting and vaporizing on impact. Imagine running through a hurricane made of lava. As a meteoroid slams into the atmosphere at over 11 kilometers per second, it compresses air into a superheated plasma sheath. That heat strips away the surface, melting, vaporizing, sputtering, like a cosmic cheese grater working overtime. Boss number 2, fragmentation. When the pressure gets too much, the rock doesn't just melt, it shatters. Like dropping a cookie versus dropping a brick. Many meteoroids have surprisingly low strength, just 1 to 5 megapascals, meaning they can crack, spall, and explode apart under atmospheric stress. The result? A meteorite shower, scattered across a strewn field. Boss number 3, deceleration. Earth's atmosphere hits the brakes hard. We're talking 0 to oh no in seconds. That G-force, it rips things apart. The Alkadov meteoroid, for example, slowed from 14 kilometers per second to under 8 kilometers per second in moments. That rapid momentum shift adds massive structural stress. Most space rocks face all 3 bosses at once. Spoiler, they lose. Over 99% burn up completely. That's why shooting stars are so common, and meteorites are so rare.
So what does it take to win? 3 things: size, strength, and speed. But not how you think. Size matters, but not bigger is always better. You need enough mass to punch through the atmosphere before you melt away. Think marble-sized minimum. But bigger? Way better odds. Large objects carry inertia that helps them punch deeper, and their volume insulates the interior from surface heat. Strength and density? That's your material. Iron-nickel rocks? Tough as nails. Carbonaceous chondrites? More like stale cookies. One survives a drop, the other crumbles. Denser, stronger materials resist ablation and fragmentation far better. But even fragile materials can survive, if other factors align. Speed is the wild card. Faster entry, more heat, more pressure. But here's the plot twist. Trajectory matters more than raw speed. A shallow angle can save a weak rock. The Winchcombe meteorite survived not because it was strong, but because its pass kept peak atmospheric pressure incredibly low, just 0.6 megapascals. Sometimes it's not about being tough. It's about taking the scenic route.
Let's test this with real stories. Chelyabinsk, 2013. A 20-meter wide space rock. Huge. Powerful. And it still exploded midair. Why? Because size alone isn't enough. Chelyabinsk was strong, but not strong enough for the pressure. It fragmented spectacularly. That airburst, equivalent to 500 kilotons of TNT. A reminder, even giants can fall. Tagish Lake, 2000. A 200,000 kilogram rock made of fragile, primitive material. Low density, weak structure. It broke apart too, but some pieces survived. How? Because sometimes fragmentation isn't total failure. If the pieces are small enough, they can slow down and land softly, like parachuting with crumbs. Another example, Sutter's Mill, 2012. A fragile carbonaceous chondrite that survived, and we recovered it fast. Why? Radar. Technology turned a lucky break into a scientific jackpot. Precision tracking predicted the strewn field, enabling rapid recovery of dozens of precious fragments. Final story, Winchcombe, 2021. The underdog champion. A weak, carbon-rich rock. By all odds, it should have burned up. But it didn't. Why? because its entry angle was perfect. Low peak pressure, minimal stress. It wasn't stronger. It was luckier. The universe gave it a gentleish ride. So let's recap the survival formula. Big enough to matter, strong enough to hold together, and lucky enough to hit the atmosphere at the right angle. And why should you care? Because every meteorite is a time capsule, a piece of the early solar system. Studying them tells us how planets formed and how life might have started. Meteorites offer pristine samples from the dawn of our cosmic neighborhood, materials untouched by Earth's geology, holding clues to water, organics, and the building blocks of worlds. So next time you see a shooting star, remember, that's a space rock losing the gauntlet. But somewhere, right now, a tiny survivor might be landing. Maybe near you. Quick question for you. If you could design the perfect meteorite survivor, what would you prioritize? Size, strength, or trajectory? Drop your answer below. And if you want more deep dives into space science, explained in plain language with zero jargon, hit subscribe and click that notification bell. Because the universe is weird, and we're just getting started. One last thought. Earth's atmosphere isn't just a shield. It's a filter, a tester, a cosmic bouncer. And every meteorite that makes it through, it earned its ticket. Thanks for watching. Stay curious and keep looking up. You never know what might be falling your way.